Hello, we are the Hattori Laboratory at Kyushu University. We are conducting research aimed at miniaturizing VR devices. Current VR devices are bulky and cause fatigue when worn. So, why does the front part of a VR device become so large? The cause lies in the VR optical system. Displays are already sufficiently thin, so the thickness of the VR optical system determines the overall thickness of the VR device. The optical systems used in current VR devices are primarily Fresnel lenses and pancake lenses. Pancake lenses are thinner than Fresnel lenses, with an optical system thickness of about 20 millimeters. So how can we make them even thinner? How thin an optical system can be depends on how short its focal length is. And a lens's focal length depends on the material's refractive index and its radius of curvature. The smaller the lens, the smaller its radius of curvature, and the shorter its focal length. Then, should we just make the pancake lens smaller? Doing so would certainly make the optical system thinner. However, it would also narrow the field of view, FOV, of the VR device. Here lies the fundamental problem with current VR optical systems. They suffer from a trade-off. Trying to make them thinner narrows the FOV, while widening the FOV makes them thicker. Therefore, we propose a completely new VR optical system, Multi-Aperture Superposition Optics, or MASO. MASO tiles multiple unit lenses in front of the eye. Since the area covered by these unit lenses determines the FOV, the width of the FOV can be freely adjusted. The smaller each unit lens is, the shorter the focal length becomes. For example, if we use 1 mm square unit lenses, the thickness of the optical system is a mere 2 mm, making it as thin as a pair of glasses. Additionally, by arranging the unit lenses on a spherical surface, MASO can achieve a wide FOV that accommodates eye rotation. Now let's talk about the core of MASO. From the explanation so far, you might have thought that using numerous unit lenses would cause the boundaries or gaps between them to be visible to the user, making it unusable as a VR optical system. This problem is solved by the superposition of virtual images. If you trace the optical paths of the virtual images obtained by each unit lens, you will find that the virtual images overlap with each other, making the gaps between the unit lenses invisible. This superposition of virtual images is caused by the human pupil, and MASO allows for gaps of up to 2 mm between the unit lenses. In other words, MASO can integrate sensors between the unit lenses, enabling eye tracking from directly in front of the eye. The occurrence of virtual image superposition means that the image displayed on the screen must also be processed accordingly. However, this processing is essentially the duplication and translation of pixels, and we have already achieved real-time processing using an FPGA. This is the MASO prototype we have actually built. This prototype uses 7 mm square unit lenses and has an optical system thickness of 14.6 mm. In addition, by arranging the unit lenses, as you can see, we have achieved a binocular horizontal FOV of 179 degrees. Considering that existing pancake lenses have a thickness of about 20 millimeters and a horizontal FOV of about 100 degrees, you can clearly see how thin and wide MASO is. This prototype has built-in eye-tracking sensors and circuit boards. Because MASO superimposes the virtual images from each unit lens, it is possible to create spaces between the unit lenses. In the configuration of this prototype, we were able to create the spaces you see here, and we embedded 4 photodiodes and 4 IR LEDs for eye tracking, along with their respective circuit boards, into these spaces. There are a total of 8 2 mm holes between the unit lenses in the center row. Infrared light from the IR LEDs is emitted toward the eye through the 4 outer holes, and the light reflected from the eye travels through the 4 central holes to the photodiodes, making eye tracking possible. As you can see, the device is extremely compact when worn. We plan to exhibit these prototypes at the Eye Zone, where you will be able to put them on and experience them for yourself. We are also considering exhibiting various other types of prototypes in addition to this one. Here is an image captured by looking into the prototype under conditions closely mimicking the human eye, along with the structural diagram of the prototype's housing. Although there are gaps of up to 2 mm between the unit lenses in this structure, the user cannot see them. By varying the pupil diameter conditions, we can capture images like this. These results prove the validity of our theory. This concludes the introduction of the compact VR optical system we are proposing. Thank you very much.